I'm, hello, I'm Julien Ledam. I'm the PMC chair for the Apache Parquet project, and I'm tech lead at Twitter working on our data platform. Today I'm going to talk about how to use Parquet, which is a columnar store for Hadoop, as a basis for ETL and analytics, and why we need that, etc. So to give you an overview of what we're going to talk about, first I'm going to talk a little bit about columnar store, why we need it, what does it provide. I'm going to give a little bit of context about what's a data collection architecture and why you want columnar format and how to use it. And then I'm going to talk about the runtime constraints and what are the things you want to put in your ETL. So first, let's talk about columnar formats and why we need to store data efficiently. So the main question is why, because we talk about storage is cheap, we talk about commodity hardware to execute our Hadoop cluster, all that, and it scales, and we can throw many machines at it. But the reality is, actually, we do produce a lot of data. And it's easy to collect even more data, and we always want to collect more data about what's happening, what's being displayed, what's being clicked on, what's being interacted with, in what way. And we have even more derived data, which is like, how do we cluster this information? What happens when we join those impressions with those clicks and see how they're used? So one way to do that is we can compress everything, and it gets smaller. But it's not just about storing the data. You want to store it efficiently in a way that the footprint is not going to be too big, but you want also to be able to query it fast and retrieve it fast and analyze it fast. And the compression should not come at the cost of reading speed. And on top of that, so often when we try to optimize a format to be very efficient, compress well, fast to access, it makes it hard to be interoperable. So the other interesting problem is to make sure this optimized format stays really easy to integrate with many things. And ta-da, enter Apache Parquet. And that's exactly what we've been trying to do, is to make sure those three design goals work together very well. That's interoperable, space efficient, and query efficient. So first, I'm going to talk a little bit about efficiency and how a columnar format enables it. So you may ask, what's columnar storage and what's different about it? So if you start from your data that has a schema, and you can see this logical table here that represents imaginary data set with 3 columns. And a row layout means you're going to interleave values for each of those columns, right? So you have all the values for the first row and the second row and so on and so forth, which means you interleave data of different types, different widths, different representation. When in a column layout, you would put all the values for the first column first, then the second column, and then the third column, which means now you put next to each other a lot of values that are the same type, possibly the same width, and it's going to compress a lot better. One benefit is going to compress better if you use a brute force algorithm like Snappy or gzip, or that just try to compress a bunch of bytes together. They're going to compress better because instead of having interleaving values of different types, they're all of the same type, they're all more consistent, and they're going to compress better. Now the other benefit is because you you encode together many values of the same type, you can use an encoding that will try to be more optimal by encoding them together. Like when you encode values like maybe A is a string, B is an int, and C is a float, you would have to use their specific encoding for each of them. So maybe the string, you put the length, and then the bytes for the string. When you do encoding on an array of things that are all of the same types, you can do something much more efficient. If you have an int, you can look at the max value of an int and start using only the number of bits you need, because maybe those are small ints, and use only the number of bits you need. And so the encoding themselves can be much more efficient and compress better because they know more about the data than a brute force compression like Snappy or LZO or gzip. And the other advantage of this is when you do a query on data, typically you don't use all the columns. You're going to select a subset of the data. You're going to say, hey, I want to count how many people are coming from this country. So maybe your data set has dozens of columns, but you need 3 to do your query. And so in a row layout, you're going to do a lot of small seeks to skip the data you don't need and jump from one to the other. In a column layout, you can do one long scan on the data and do a few big seeks, and it's going to be much more efficient to retrieve that data from disk. So as said, you can use better encodings for those data sets. And one thing to think about when you want efficient encoding, and here it's efficient in the CPU sense, that are going to be fast to decode, is to think about how modern processors work. And modern processors don't execute one instruction at a time. What they do is they decompose each instruction in many operations so that they can start processing the next instruction before the previous one is finished. And to do that, they need to predict what the next instruction is going to be. So like dozens of instructions of the future, they need to know what's the next one coming so that they can start processing them in parallel and not just exactly one after the other. So some things to pay attention to when we have those very efficient encodings is to have highly predictable branching. So things like simple loops, all they do is looping on an algorithm that has no branching at all, so that it's very predictable which instructions are going to happen. And typically the processor can predict that we're going to do many times this loop and maybe wrong the last time when we're done doing it, but it's negligible overall. The other thing is how the CPU is using cache, and the fact that the size of the cache is limited. And so by working on one column at a time, we can also be more efficient by reducing the working set. Instead of having all the data for everything, you can work on one column at a time and be more efficient using the CPU and the cache. And so depending on the type of the columns, we can use an encoding that is the right tool for the job. Delta encodings are used for encoding integers. And so it's all about encoding the difference between two different values rather than the absolute value. And typically, if you have time series, let's say you're measuring the latency of your service or something of that sense, the variation of the value is actually much smaller than the absolute value. So you can encode that instead and be much more efficient and using a lot fewer bits to encode this data. Prefix coding is delta encoding for strings. Dictionary encoding is about using redundancy in the data, like if you have a country column or a host name column, which is a host where the request is coming from. There are actually going to be a small number of these, and small being like tens of thousands. And so you can build a dictionary of those values and encode them as int again, and again take advantage of being able to encode integers instead of variable length values. And finally, run length encoding is about, instead of encoding 1,000 values that are the same, you can say we have 1,000 times the same value and be more efficient. So if the data has a lot of repetition, as happens often, like if you're doing cubing on data or things like that, it's going to compress really well. And so those are examples of some of the things you can do when you look at each column independently, and encoding independently and can do things much more efficiently. The other aspect of encoding data in a columnar format is you need somehow to get to a flat representation of columns. And often in Hadoop world, we have nested data structures. So we don't just have flat schemas. There's structs of lists, of maps. And so what we use the algorithm described in the Google Dremel paper to turn those nested data structure into a flat representation. And we do that by storing extra bits, which are the repetition level and definition level next to each value. And that compresses very well. And really, when you think about it, it's just a generalization of using a single bit to encode if a value is null or not, except in that sense, we encode also the depths of the repetition if it's a list, or the depths of the null if the null happens somewhere down that tree. And it's a little long to explain, but you can go see this blog post where I described it in details if you want the details of this. And so to summarize, you have this table that you can imagine, this two-dimension column. And most of the time, you do a query that uses only a subset of the column. So that's our first illustration here. I'm reading only column B, so I can read only column B. And because it's columnar, it's easy to do that. And also because we store statistics about row groups and groups of rows, you can also skip entire chunk of the data if we know in advance that the query doesn't match any of those entries. And so you can do horizontal partition and vertical partitioning together and reduce the amount of data you're reading to only the ones you need, and reduce I/O to only the data we need to read. And often we cite deserialization as a cost of reading data. And the best way to optimize deserialization is to not need to do it. So it saves I/O because we don't have to read this data, and it saves CPU because we don't need to deserialize and assemble this data. So now a little bit about interoperability. So another value of the Parquet format is that it's been designed to be really interoperable and across languages. So that's why we have a file format that is defined at the binary level, and there's a spec. It's not just defined as the Java code that is in the repo. There's a spec for it, and it's defined at the binary level, and we have implementation of it in Java in the Parquet MR repo. And Impala has a full implementation in C++, and we also have a repo with implementation of the encoding in C, so that it's really language agnostic. So that's the first level of interoperability. Then the second level of interoperability, we implemented the whole assembly algorithm, all the logic I talked about encoding efficiently, decoding efficiently, assembly algorithm of building those nested structure from this flat representation. And we made it in a way that it's highly interoperable in an efficient way. So instead of having its own object model and kind of materialize its own object model and then convert it to another abstraction, we have an event-based abstraction here. Right here. That makes it easy to integrate with everything. So instead of creating an object, we just say, well, we need to start an object, a little bit like a Sax-based API for those who've known XML. And that enables to integrate with many, all those different object models. And also, if you're doing a SQL engine, or if you're using a SQL engine on Hadoop, SQL engines will tend to integrate at a lower level and try to push the assembly as part of their execution plan to optimize using the columnar format. And I'll get back to that. So thanks to this, Parquet has been integrating into many, if not most, of the existing framework and query engines in the Hadoop ecosystem. And that's been one of its big successes. So now I'm going to give you more context about when do we use Parquet, how do we use it. So let's start with typical data flow. So I'm assuming you have some kind of service that is used by someone. And it can be, it could be a website, or it could be some API, some service, a platform. And it has some like stateless part of it, and there's some stateful stores that you're using. And now you want to know what's happening with this. You want to extract data from it, whether it's for getting insight of what's happening with the service, how people are using it, or you want to build features off of it. Like Twitter has a who to follow, which is based on the data, right? So based on what people are doing, we're going to suggest other people to follow. So one of the main things to think about is there should be a schema for how you instrument and collect logs. And you will have some kind of streaming infrastructure, typically Kafka or Scribe or Chakwa. Kafka is a very popular one, to collect these events. And you can also have periodic snapshots to get your mutable stores, like maybe it's user profiles, and you want to regularly dump them so they can be joined with clicks over there. And so you would have the string, want to do real-time analysis, and the batch consolidation to be able to do analysis in the past, what happened in the past 6 months. And once you've collected your data, you will typically have two aspects of it: the streaming, where you use Storm, Samza, Spark streaming, some of those things. And you have the batch environment. And in there, you need a query efficient format. That's where Parquet will live. And that's where you can do a lot of different things: graph analysis, machine learning, SQL and Hadoop, a lot of those tools, automated dashboards driven by Hadoop. Oops. Sorry, I think I clicked on the wrong thing. Thank you. And in the end, you have happy data scientists, however you call your analysts, to look at this data. And that's one example. As I said, you may use it for analysis and understanding, getting insights, but you could also use it to build features. So I said one of the important things to think about is schema management, because you're logging all that data and you have a lot of data in different types. And one important thing to think about is how you're going to describe your data. And Hadoop does not define any standard for defining schema, but there are many available: Avro, Thrift, Protocol Buffer, Pig Hive, and they are all different. And what they provide two things. They provide first a schema, which is how do I define the structure of my record? Is it structs of lists? What are the constraints of the type? Is it null or never null? Is it required? Things like that. And it also defines a row-oriented binary format. And typically, that's what you use in your streaming part of the infrastructure. What they don't define is a column-oriented binary format. So what Parquet provides is a column binary format for storing this data by reusing this same schema. So you reuse the schema base from one of those tools for schema management you picked, whether it's Avro or Thrift or Protocol Buffers or another. And we will reuse this schema, and the row-oriented binary format can be the same, and then we optimize a columnar-oriented format for query analysis. And to give you an example and give you a taste of the difference in those tools, if we take the simple example, we have an address book that contains several addresses that are fields: street, city, state. I'll give you a few examples of how they look like. So this is a protocol buffers example. It's very simple. A model when you can group. The group type represents a struct, and every field has an ID. And you model list by having repeated fields. So a field can be represented more than one, and that's how you model list. Thrift is slightly different. You have a notion of struct. It has a list of fields. Fields are either required or optional. And complex type includes list or set as well. So that's how you represent a list, by using a complex list type. And Thrift and Protocol Buffer are similar in that you need binary compiler to generate source code in many different languages, and they're language agnostic. And there's a common standard format that don't depend on any of the name of the fields, because all fields have an ID, and the ID is what's used in the serialized row-oriented format. Avro is the latest of those. I created quite a few years ago now, but it was a newcomer at the time. And similarly, so the IDL is in JSON, and there's also a different IDL representation now that is more compact. And some variation is it also has the notion of record, which is basically the same thing as a struct. You have fields that have a type, And the way you encode that something is optional is by saying it's a union between a null and some other type. So null is actually a type. By default, things are defined in Avro. And another advantage of Avro is it's all in Java. And so the compiler is Java. So it's easier to integrate in a Java project than protocol buffers and Swift are. So now, assuming we picked one of those, we do the initial log event collection. And one of the things to pay attention to when you collect this data in your streaming is, at that point, you really want to sync to disk as early as possible to minimize event loss, right? So you have events one by one coming. You want to store them. So it's not there at that moment yet that you want a columnar format. For now, we really want to be row-oriented because we're streaming. We want the lowest latency to get our data, and we want to be able to be streaming analysis as well. And also, it's probably a good idea to count events when you produce them and when you consume them, because there are many ways this cloud of services I'm putting here could be thousands of machines, depending on the size of your infrastructure. And the more machines you have, the more possibility you have of losing events, have some machine misbehaving, not doing the right thing. So having some kind of measurement of how many events you're losing is important. And now this other circle is showing where we're actually converting to columnar storage. And one thing to pay attention to is because when we get these events one at a time, or one row at a time, if we want to be able to convert them to a columnar format, we need to buffer a certain numbers of records at a time, because you're going to write the first column first, then the second column. So before we can start writing the first column, we need to have all the records for this column in memory. So this one is better executed in batch mode, and you have like something hourly, consolidating, converting, and hourly, or every 10 minutes if you have a lot of data, or if you want this, reduce the latency of this, and storing the data in a columnar format, which is more efficient for batch analysis. And when we're generating this data, so that's part of our ETL, right? That's how we collect data and we store it on Hadoop for later analysis. So here we're talking about storing it in columnar format so that you can read one column at a time, be more efficient at reading. The other things we need to think about when you're doing that is potentially doing dynamic partitioning, changing the sort order, sorting the data set in an order that's going to make it more efficient, and generate stats. So remember that the Parquet format stores stats like min-max for each row group, which help when you do a query, when you filter on something, to understand this filter and to read only the row groups that actually have a chance to match this filter. So if you change the sort order or you do dynamic partitioning, that's going to make this stats collection even more efficient and make a query even faster. So those are some of the things to think about when you're actually converting your data. You want to make it efficient for query analysis and for storage. So here are some examples of how you write to Parquet. So the first line is about MapReduce. It's fairly simple. You pick one of the output formats which is integrated with the object model you want to use, your schema definition. And all you need to provide it is the class that represents your schema. And you give it Avro objects or Swift objects or protocol buffers objects, or you can do it with Pig as below. And it's going to store it. It's going to look like it's writing Avro objects, for example, but it's going to store them in an efficient columnar format. And you can do that with MapReduce. You can do that with scalding in a similar way. You can do that with Pig. And Pig will infer the schema from the input. Or you can do that with Hive, Impala, or another query engine. So that's how you write to Parquet. Typically in ETL, you can do it with MapReduce or like more code-oriented tool, and then you query more with a SQL engine. So now I'm going to go over some examples on once you have stored your data, how you can query it. So if you use something like scalding, and scalding is a Scala DSL on top of cascading, That's how you would define your input. And so once you define your input, like up here, you can do operation on it. So if you're familiar with functional programming, things like Spark or Scalding, this will look familiar, right? So you can map on your data set, define some transformation, do group by, joins, etc., and save it back to Hadoop. And some of the things that are important to look at here is, so you're reading some data set and it has a type, here the address book. And in a Scala API, we added some APIs to enable projection pushdown and filter pushdown. So that's where you define a predicate with a special API, and because Scala lets you override operators, it's actually more an expression tree that represents your filter rather than the actual execution, and that's going to be pushed down to the statistics and read only the data that's needed. And also we are going to read only the columns that you care about in this example. So in system like Scalding, you need explicit pushdown. If you're using Pig, all you need to do is to use a Parquet loader, and you get your regular Pig tuple if you use the Pig. And because Pig is more a self-described language like SQL, the optimizer can actually figure out which field you're accessing here. It sees that you're accessing A, B, and C, so it can push down to the storage layer, then only those columns are accessed, and it's going to read only those columns from the physical layer. So that's where it's important to push the assembly and the reading of the data as part of the plan of the query to make it more efficient. And the same thing, we can do the same thing with predicate. Like if you have a filter, we can understand the filter and optimize reading the data. And nowadays there are many SQL engines, and I think I forgot Tajo. There's also Apache Tajo, which is another contender. And so the load is typically in Hive, Impala, Presto, kind of, you just create table as, like you do in Hive, as Parquet, and then you can query it. And because it's a self-describing language, filters or projection pushdown can be pushed down to the storage layer. In Drill, Drill has the option to query Parquet tables directly, so you can you give it a table name that looks like DFS dot and a path, and it's just going to infer, read the schema from the file or from a set of files, and execute the query directly on it. Spark SQL, in the same notion, you can do based on Parquet files, and you can integrate your queries in your Spark job. And the advantage of this approach is something that is neat, and you can do a query, and then you just pipe the result of it into a regular Spark data. So you can combine together something that's very expressive about selecting your data and doing some hardcore code and more like transformation on nested data structures and so on. And now I wanted to talk a little bit about the Parquet community. So Parquet started in fall 2012, and at Twitter we were building a prototype of a columnar format. The Impala team at Cloudera was doing the same thing, and thankfully we connected and we merged our efforts, and we said, like, really, we don't want many of those, because we need the execution engines to deeply integrate with those, with the columnar format. So we want to make a standard format that's going to be integrated with everything and being a standard and easy to integrate. So that's how we started. In March of the next year, we announced it as an open source project as it was reasonably advanced, and we had standardized how we wanted to do Java and C++ interoperability, and how to implement Thrift and Pig and other things. Criteo, which is an ad retargeting company, signed on for doing the Hive integration at the time. In July 2013, we did our 1.0 release, and we had already 18 contributors from more than 5 different organizations. In May of 2014, we joined the Apache Incubator, 40 contributors at the time, and recently we graduated and we're now a top-level Apache project. And companies like Netflix have been very supportive of the Apache project, and they're doing many contributions, integrating it much better with Presto. And the Drill project, Apache Drill project, is building around Parquet, and the Spark SQL is also using Parquet a lot. So I haven't updated that graph, so it stops in April 2014, so more than a year ago. But that's how we do the open source announcement. So here you have like pretty much myself and a few others. Open source announcement, 1.0 release, and its number of contributors has been steadily up. And I really need to upgrade that graph, but it requires some Git log digging to build. And so that's been very successful. And so if you want to get involved, there's the Parquet mailing list. We have the GitHub repo, where you can see pull requests and see discussions happening. There's the Parquet Jira, where the tickets are open, and sometimes we label them with pick me up if those are things that people are welcome to come and contribute if they want, or if you have ideas or needs, you can also mention them there. And we also do regular meetings on Google Hangouts to it helps stimulating progress. And if someone has really a priority on some features that needs to be happening, they can raise awareness about it. And now, if you have questions, I'll be happy to answer them. And please, because this is being recorded, come to the microphone so that we can hear your question.
Yeah. Thank you very much for. This is not working, seems.
Yeah.
So thank you very much, for providing this awesome platform for doing this transformation from many of these formats to Parquet, which is actually very good for doing many type of queries, which you went over that. So my question is that we have very structured schemas, and this schema could be deeply nested. So how do you flatten that when you save it into Parquet columns?
Yeah, so we do have the same thing. We have some data sets that are deeply nested. We use Thrift at Twitter. And so the way it works is you can imagine if you have a flat schema and some of the columns are nullable, the way you would save whether this value is null or not, you can use a bit set. And for each value, you store 1 or 0, whether it's null or not. So you could say 0 means null, 1 means define. Now, if you have a nested data structure, instead of storing 0 or 1, you can store at which depths. You have one column per fields at the end of your tree, which is your schema. So all the leaves of that tree, only primitive types have a column. And so instead of storing if it's defined or not, you store at which depth it's defined. So let's say it's 3 level deeps. 3 means it's defined. 2 means it's null, but the field right above is defined. 1 means the other one. And 0 means, well, your row is empty. And so that's for nullability. And then when you have lists inside of these nested data structures, let's say you have 2 levels of lists. You have a list of lists. Then the repetition level is the second bit we are storing. And basically the way it works, if you have a new list of the first level, we store 1, which means it's like a marker. This is the first element of the second list, of the first list. And if you have a new list at the second level, we store 2. So basically, it acts as a marker. As long as, so it would be more 0, 1, 2. As long as it's a 2, that means we're in the same second level list. So we store 2. Once we have a 1, that means it's a new element in the list of first level. That means we create a new list of second level.
I see.
And so it's first element. If it's a 0, that means we need a new list at the first level. And so the advantage of storing the information that way, so by storing those 2 small ints, we capture the structure of the record. We know if we need to start new list at what level, and we know if we have a null and at what level. And because they're small integers, they encode very well. You can use only a few bits. They're bound by the depth of your schema. So it's going to be 3. 3 means you can use only 3 bits 2 bits to store this information. And really, you can use those same efficient encodings. And if you have a lot of nulls, you can use run length encoding and say, we have 1 million nulls in this, and it's going to be stored very efficiently. Or otherwise, we can use bit packing and say, we use only 2 bits per value to store whether it's null or not. So that's how it works. And that's make it very efficient to store this information.
Thank you.
You're welcome.
Yeah, so I was wondering if you could spend some time talking about what the storage to HDFS. So you're buffering the data, transforming into Columnar, but you have to make some decisions about block sizes and splits and the replication. So could you spend some time discussing issues around that?
Yeah, so the way data is laid out is, so your data set is a bunch of rows. And because we need to buffer the data in memory before writing it in columnar format, the data set is split in row groups. And a row groups is a certain number of rows that's going to fit in memory, and then we are reorganized in columnar format. And then in each row group, we call column chunk, the chunk of the column for that row group. And in that column chunk, we split it in pages, and each page is the unit of compression. It's how much we're going to compress at a time. And so I'm talking about those because that's where you may have to tweak the size of those. So a page should be big enough so that the compression algorithm works well, because if it's too small, the overhead of compression is not going to be working very well. So typically something between like 64K, 128K is kind of the minimum for those. And if it's too big, then you lose in granularity. We have statistics also for those. So you want to have them as small as you can so that you have granularity on the data, but still take advantage of compression. And row group, the limit is how much memory you can use on write time to encode it. And it's really the compressed size, right? So we buffer it compressed in memory. So that's your limit. And you want them as large as possible so that you can optimize your reads, your scan. And in that sense, they should be at least like order of magnitude, like around 1 gig of size, typically. So they could be smaller than that, right? They could do 512 megs or 256. That's fine too, but larger you would get more benefits. Also, the other factor that to take into account is the number of columns, because in a row group, it's really you want the column chunk to be as big as possible, and which means the more columns you are, the more you have to split this budget for writing row groups. And so that answer your question. So that's the kind of thing you need to think about. And we said HDFS, but a lot of people use Parquet out of S3 as well, right? It's not married to HDFS. You just need some kind of distributed file system, and Parquet is a file format. So you can put it in a file system.
Quickly, for the interoperability, if I write out thrift records into Parquet, can I read them back as protocol buffers? Do you like
you
store?
could. So I don't think you need some kind of mapping to make sure everything aligned. I don't think anybody is doing it today, so it would need some verification. I'm sure there's some corner cases, but we've been standardizing all collection and stuff so that it's possible.
So how does it work with the query engines? If I have like a MapReduce job that writes records from thrift to Parquet, the query engines need to know that it's thrift?
No,
Parquet.
they don't. So basically, Parquet has its own schema, which is really close to protocol buffers. So actually, you would have to define your protocol buffers so that it matches the schema. But so thrift to protocol buffer, it would definitely work. So basically, we map the thrift schema to a more protobuf-like schema. That's what's stored in the file, and we keep also the original thrift schema so that we can map it back to the thrift records. But from there, you can read it. You have the same format and the same data if you write from Avro, for example. And then, so it's more about making sure you can map exactly to the type. So in theory, you could do it, but there may be some corner cases. We've been working on making sure collections are mapped exactly the same in each of those languages.
Because POJOs too, right? That would be.
POJOs, there's the pull request for POJOs, but it's not been merged yet. So you could do it with POJOs as well. And so it's all about being able to map the Parquet schema to the other schema. And yeah, definitely that's the kind of thing you could do. Yes?
So first of all, thanks, Julian, for coming up with this great format. It works very well for most of the cases. So I had two questions. The min-max filter per column per row group, it works very well when for that row group the columns value range is small. But if it is wide, it might not be effective. So I'm wondering if there are any efforts going on to alleviate this problem, say by storing multiple ranges. And the second question was, like, there are some use cases which could benefit if for some columns, if you could create an optional index, like if the format allowed a complete index
so
for some
we're
columns.
running out of time, so I'm going to do a quick answer to that, but I think that's our last question. So just quickly, yes, there's some effort to do also page level push down on this. Other things you can do is, as I was mentioning, you can do some reordering, maybe sort your data set first, or do some dynamic partitioning to kind of store based in a way that it will make those statistics better. Indexing, there have been some discussions about it. There could be also external indices, but I've not been working on it just yet. Thank you, everyone, and it's been fun to talk to you. I hope you got something from this. Thanks.